But anyway, this is the sax instrument. As I mentioned yesterday, this was built and pretty much designed by Yuli, myself, and Miguel, except for the source, which we bought, and the detector, which you can kind of see if you stick your head in a little towards the back. So if you look at the little hole, I want you to notice that on the sides of it, there's a railing system. Basically allows the detector to slide back and forth, and this detector is in back.
Sorry, what are we looking for when we're looking inside?
What?
What are we looking for when we're inside? Like what are we looking at?
Oh, just the detectrons usually have around 3. Fun fact, the slits that are used around the world were invented by Yuli. Like, yeah. These scatterless slits that are like, basically, so before they used to use like acid drop pinhole slits and they were circular, but unfortunately anything with electrons scattered, so when you're cutting the beam, it's very hard to have something that the slit itself is not going to scatter. So parasitic scattering just existed. Like, it was kind of something that would, like, you know, beamline scientists would have to spend hours and hours every day trying to realign the beam so that you wouldn't get this smear right next to the beam stuff. Anyways, Yuli invented slits. They're very simple in design, but basically you take a silicon crystal and put it on an offset on its cut, and if the surface is extremely smooth, there'll be 0 scattering. So now you're able to cut the beam however you want without any parasitic scattering. But yeah, anyway, so now pretty much all synchrotrons and it's very weak. You don't have many answers. So you guys can see. Okay, so samples in sacs come in 2 forms, either liquid or solid. If they're liquid, they go in capillaries. If they're powder, they usually go in capillaries. And if they're solid, you just stick them on them. Basically, capillaries are down here. They're basically these quartz tubes. This one's empty. And these ones are specifically 1.5 millimeters in diameter. The optimal length for solution scattering for sacs. You can pass it around and get it if you don't know what they look like. But they're very, very thin-walled pieces of glass.
You said they were quartz. Is it
quartz.
like how do you make a capillary out of quartz?
I do not know. All I know is that they are like hand drawn, so like, there's actually a variability in thickness. Like this one's a lot thicker than that one in terms of like size. They have to like start up the factory every time you order a set. You know, but the important thing is that they're only 10 micron wall glass, so it's effectively not. It's intentionally small walls so that you have very little scatter. Because anything with electrons scatter, which is a lot of things, most matter. Ta-da. And then it slides in like so. It's silver DNA. I had it in the PowerPoint. It's a standard that's used a lot in sacs for sample deterrent. It's basically a 1D crystal. Okay, so common questions that everybody usually asks. This is essentially more than enough. That is easy to align with and way more than the size of the beam. I have hit like pieces of feather. Like I've mapped, one time I did a project mapping how the different anatomy, like the rachis into the quill into the rachis into the barbs and barbules, and you can hit very, you can make it work. But ideally, your scattering signal scales with the volume. So the more that you have, the better. And so basically, however, if your sample is larger than the size of the beam, it doesn't do anything. So the beam by default is about 1 millimeter big here, and we can set it down to 200 microns. 200 microns is about the size of a synchrotron beam normally. So like that's usually the size that you're. I mean, I shouldn't say that generalized. It depends on what beam line you go to, but generally they're around 200 microns. I'll say a little less, but it's bigger. And then, but anything larger than that is essentially invisible to the experiment.
The powder also goes in that capillary?
Yes, yeah. So the powder goes into this capillary, and you'll notice that the amount I filled is much larger than 1 millimeter.
How do you fill the powder inside?
You pour it in the cup.
So difficult.
Yeah.
Powder, right?
Yeah, it's powder.
But it has like an open ended. Yeah.
No, that's it's a sealed. It's like the pinching of the glass. But yeah, so this is way more powder than you would ever need actually. Like literally just 1 millimeter is enough. It just makes alignment a lot easier.
Do you have different type of sample holder or just?
Yes, yeah. So there's a whole toy box full of them right here. So like this one would be like a stop flow cell, which I can remove the lid, where you load in the solution and then syringe it up.
Oh, that's what I'm going to ask you, because what about if you have like a very difficult solution?
Yeah, exactly. Then we'll get into that because I have some very. But like, we can also 3D print ones where you like. So some people use washers. If you go to ALS, usually they use this size washer, and you just stick them in like so. And then there's raising incidents. But anyways, there's a whole bunch of different ones depending on what you're doing. But for this, that's enough.
What is the material of this tunnel, the white one?
The white one? It's a very long. It looks like this. There are links to some. Let's see. Essentially like this. Wow, it's so much smaller. Okay. So one of them looks like that, and the nice thing about them is that they form this nice chain crystal structure that will create a nice scattering pattern. Okay, why is this not? I'm just going to switch. Actually, attenuates it. And also creates scattering, which is kind of annoying. However, vacuum is even more annoying. So like, for as a user facility, like if you buy a commercial, let's say a Xenon system in-house access, it's only a vacuum. It makes better quality and it's easier to engineer. However, you run the risk of if something breaks inside vacuum, you have to like completely clean it out and make it. So we have a little bit of a trade-off. So basically, this is under vacuum, this is under vacuum. This area is not under vacuum. And so basically, you will get air scattering from this little wind column. So since it's open, I should point out, okay, so here is this buoy, and yeah, so what you're seeing here is a live feed to this camera right there. And there's a mirror that's spaced 45 degrees. Right? On the GUI, you'll see that it'll tell you that it's at low power. So we're going to first just click the button to power it up to high power. This takes a couple seconds. What?
Did you write?
Yeah, I wrote the code. I wrote the code. It was a fun project. Did it during COVID.
Took you like a day or something?
Oh no, it took me a button and then start loading your sample. So basically all it's doing is it's just aligning the slits and the mirrors. Basically there's a whole bunch of different mirrors and objects that are slowly moving and it's just aligning so you have the maximum outcomes.
The red speck we see, is that from what is it called? The red dot.
The red dot. Oh yeah. So there's a black dot and a red dot. The black dot is the hole where the X-rays are coming out. However, the camera, it's really hard to create zero parallax. So the red dot is actually where the X-ray beam is on your sample. So we'll see for alignment, the X-ray beam needs to hit your sample. So we are going to make the red dot hit your sample. Yeah. Yes. The way it works is you turn it all the way to the most sensitive setting, and then you point at whatever you feel unsafe. So I'm glad that the demonstration didn't just suddenly spike, because that would have been horrible to get on video. But yeah, you can basically, it's important to compare to background. So this is at its most sensitive setting, so there is X-rays and cosmic microwave that is hitting us right now. So there is some, you just point and compare, and as long as it doesn't spike, you're fine. EH&S comes very frequently to check to make sure there's no radiation. They call it scan the X direction, and basically what it's doing is it's plotting the number of X-rays that hit the sample as a function of this. So, if I had a little pen, okay, yeah, this is a large capillary. So we were here, we moved it out of the way, and we're measuring how many X-rays are hitting you. The capillary is completely out of the way, so as I move X, nothing changes, and I have the direct beam. As it starts to hit the capillary, you get less and less until you're in the center, and then it starts moving out, and you get more, and then it flatlands again. So, pop quiz. Oh, you're videotaping, but where actually fill in the coordinates, and if you want to move to that position, you can click move, and you'll see that it now aligns more accurately to the center of the capillary. We could scan the Z, however, that would be kind of pointless, non-eventful since it's so long. But you now need to just give it, we're almost there, we just need to give it some parameters. So it's going to ask for the Q range. So I will enter in 0.007 to 0.2. I will explain kind of this as it runs. But you're going to want to do that, and you're going to want to give it a runtime for how long is the exposure. So 5 minutes will be fine. And then you want to give it a sample name. So I guess I'll just call it AGDE 5. And also you want to tell it what folder to save the data in. So if you just click browse, or data, I'll create a new folder for us. BioPacific Summer School 2025. Create, and click save. So we now have the file name, scan range, how long, and we click accept. You'll see it gets filled into this queue. So now if we had more samples loaded into this, you just repeat the process n times until you're happy, and then you...
What is the queue minimum and maximum?
I will explain that difference. Yeah, but it'll be, it's easier to explain as it's going. So you click run, it'll move to the position, it'll move the detector to the right location, and then it starts.
It can be automated, like a measure sample one.
Yeah, that's what. Yeah. You basically just add it to this queue, and it'll do the entire queue. So what I want you to see here is that you have 2 pieces of data shown to you in live time. So this is the current reading of the detector. So you can think of the X-ray detector as essentially a camera that's detecting X-rays instead of light photons, and then here is the reduced data on the right. So this is like the 1D data that you normally use for publication. So now to kind of answer your question, right? So you can see there's an image and then there's the graph, and basically Q is a measurement of almost like the radius, like how far from the beam center is the data. Kind of right? And what's being plotted here is the average number, the average intensity as a function of Q or as like a function of R almost, right? So like this ring, that peak corresponds to this ring. And this second peak corresponds to this second ring. Basically, you just want to make sure that the sample is cool.
Yeah.
So what you do? You are mounting the sample on this.
Yes. So basically, I mean, as I said, anything that's larger than the size of the beam is invisible to the experiment. So like, technically you can you can hold it with your hand over if you want. like it really doesn't matter what's going on. So like, the easiest way is just to tape it onto something and then stick it in.
And what is this material?
Oh yeah. And then this one, the material is actually a little harder. It's that little part right there.
And what is this yellow one?
Yeah. So I'll say that in 1 second. So basically it's Kapton.
Carbon?
It's just Kapton tape. Kapton tape. I'll explain. It's not the sample. I'll load it and then kind of explain. What we have is here inside the blockopolymer. Like we basically have blockopolymer samples, and they're kind of like this really viscous liquid. So it's hard to get inside of the capillary.
Did you like spoon?
Yeah, exactly. So most commonly, you usually put them inside of washers, and that are just like in between two pieces of Kapton tape. It doesn't have to be, and sometimes it's just an envelope. Like you just spatula it in, fold it on itself, throw it in the beam. The reason why you use Kapton is because, one, it's readily available and cheap and easy to use. Two, this does a lot of they do a lot of temperature experiments, so like you want something that's like a little more thermal resistive. Three, and most important, it is an amorphous polymer. You want something that's amorphous-ish as your like well or window, because it's going to scatter.
So the ring thing is the Kapton?
This orangish, this is the Kapton, and that's just a metallic washer. The sample is inside filling that well.
So your sample, what if it doesn't fill exactly like the whole circle?
As some of these don't, it doesn't matter. Okay, so like I said, the beam, as long as the sample is a millimeter big, it's fine. Within a millimeter, you need to make the beam smaller. It's a big if. Because your data is going to look very bad. So we're just going to write down the peak positions. So 0.109. And then we have one at 0.219. Or 218. Yeah, 0.218. Yeah, those are the different. There we go. That way I can talk about it as this one. So I'm going to click close. And then we're going to click continue. Okay, so now let's, I will align the first one.
Okay.
It'll only move the x-axis. So, because I already aligned these, so you should click on the, and then, so you just roughly get it there and then click scan the x-axis. So click on X.
Yes.
Yep.
Okay.
And then just click begin scan.